Hi, in this session we're going to talk about how to take a bump test and convert it into numbers. Those numbers are what you use to come up with tuning parameters. So hopefully you're coming into this session self-regulating process identification with an actual bump test where you have a printout would be ideal, or something in Excel or some numbers, and if not, after this you'll be able to go and do that. But we're trying to identify numbers, two numbers, that represent how the process will respond if I inject energy into it. That's the trick. Once you identify that and it's repeatable, you can tune anything, and that's the first step. So we're going to do a quick review here. We're talking about a process. This can be any process, not just this heat exchanger. Anything that has an input and an output relationship, where you go and you can inject energy, whether it's a valve change or a gate change, or you change an output. And remember, what we talked about is work with your operators. Make sure you don't bump in the direction of the defect limit. Make sure you look over historical ranges to see how much change has been made, and start small. If the operator says 5%, maybe start at 1% output change, and then gradually go up until you understand what the dynamics of that process are. If you have a process that you just can't do a bump test on, there are other techniques, and I'll show those later. But I do recommend that you identify the process dynamics. I would even recommend, before you even start doing the bump test, that you do a visual inspection of the actuator and the instrument and the process that you're going to control. There was one example. I went into a control room that had a history of people trying to tune a pretty critical control loop. And the operators were pretty dejected. The plant operations was down, and they said, you need you to go in there. So I got on a plane and I showed up. And they said, well, here's the system, here's the control loop, we want you to tune it. And I said, well, before we do that, could you take me out on the floor and actually show me the instrumentation and actuation device? And they looked at me they're like, what? And I said, well, I need to see it. I need to get a mental picture of what I'm actually moving. And as I was walking out, the operator told another operator, when he didn't think I could hear, he said, this guy's going to fix the problem. Don't ever assume that you know that the state of the actuator and the instrumentation. You need to take a minute. Have the operator show you. I had another example where the operator said, well, this is the control valve that we move. Well, he was moving it, and I was looking, and I said, well, that goes down into the basement. Let's go look. Somebody had cut that line off. He had been adjusting an actuator that never went anywhere. He was very embarrassed. And he said, well, no wonder nothing's happening. Processes change all the time. Take a minute to walk outside, if it's safe, to look at the control plant, the actuation device, do a visual inspection of the actuator, look at the packing material, I've seen valve positioners that are open and they're full of dirt. I've seen cases where they've gotten water in their airflow and they've got rust. You need to take a minute don't just think you can fix everything through software and these nice operator displays. Sometimes you need to do a visual inspection. So now we understand our process, we understand the operator, we've talked to the operator, and we've injected energy. Now here's what we're saying is I injected energy, and then we've recorded this change. Do you remember from the last session what classification this is? Remember we said there were 6 classifications that all loops fell into. There's pure gain, there's first order, there's second order overdamped, second order underdamped, integrating, and first order plus dead time. I've included that picture here for you. Which one of these pictures, and I've shown, which one of these pictures best matches this? What type of process is it? What's the classification? Well, it's a first order lag. Now that you know that it's a first order lag, we will show you how you would identify the process dynamics. In this particular session, we're going to cover these 3 sessions here. We're going to cover a pure gain. We're going to cover, they kind of an additive. Once you know the most basic one, which is pure gain, what are the model parameters? The last session was how do I do a bump test? How do I understand what a process dynamic is? Now what we're trying to do is identify numbers that represent those dynamics. So what's a pure gain? First order lag, what is it? How much, how long? Then this one is, well, I made the change back here, but it took a while, and so there's delay. And then we'll hold this one off for another session. These two can be approximated. Remember we were showing model error or model mismatch. So you can even approximate these two as a first order. So this session is going to cover a lot of ground, all right? And that's what we're getting into. So hopefully if you've got your paper, if you've got your bump test, that's great. Let's play with that now. These are the models, pure gain, first order, and first order plus dead time. We're going to come up with the objective here is that after you've injected energy, you got a predictable response. That's the other thing. I don't recommend that you just do one bump test. Do a few of them to see if you get the same shape. If you have a bad valve or a nonlinear pressure or a header, you'll get different results with the same input. Think about driving a car. If you change the steering wheel and get a different radius each time you move it, there's probably a problem with the transfer case. Same thing here. You're looking for repeatable responses. So when I give it a known input, I get virtually the same change each time. I recommend anywhere from 3 to 5 bump tests in order to identify repeatability. Did my process respond the same way every time? I've seen too many cases where a guy will do one bump test, he gets this pretty response, I've got it figured out, he goes and tunes it, and all of a sudden tomorrow it all goes to pot. Because the process changed or he did something wrong. So do a regular basis, do 2 or 3 of these bumps, and once you get repeatability, then you know, okay, I've captured the dynamics, I've captured the essence of this particular process. Now, don't get scared with this. We're now starting to introduce math. The way you read this is y is our measured value as a function of time is equal to our actuator change u as a function of time times a modeling parameter. We call that a gain, k. K sub p. That's how you analyze this, k sub p. If you're an ISA member, you'll understand that ISA naming, Instrument Society of America, has naming conventions. This is a lowercase p. Lowercase p's are aligned with the process. If it was a capital P, it would be a proportional gain. That's where it starts to get confusing, and I'll try to navigate the waters here. But you have a subscript. The subscript tells you the type of gain. K, I've seen it as K, I've seen it as G. Those are the most common gain indicators. But it's strictly a multiplier. So you can see here, if I change the input, then I change the output, they look the same. They're only different by scale. That's all this is a scale change different. But what, in English terms, I've got it in parentheses here. How much did it move for a given actuator change? If I moved the actuator 5%, did I get 10%? If I moved the actuator 5%, did I get 1%? That's the process gain. Think in terms of actuator size. I know that's not exactly right, but it's real close. It's how big is this actuator? Imagine filling a bucket in your house with a garden hose. Or you have the fire truck come and he's got a fire hose. They both move them the exact same amount. Which one is going to fill the bucket faster? With a garden hose, you may make a little change. You're open it the whole way. With a fire hose, it'll blow your shoulder off if you open it the same amount. That's process gain. I like to think of it as how much power does my actuator have on the process? Do I have to change the process 50% to get a little bitty change, like on a garden hose? Or do I change the actuator like a little bit and get this massive output? So valve sizing plays a part in your process gain. That's just some things to think about as we go through here. How is this calculated? How's the math? There is math here. So what we're talking about here is I'm looking at my input, which is, again, my triangle, my delta U, my change in actuator, as opposed to the change in the measurement. So the gain calculation for your process is defined as the change in process, here, divided by the change in its input. And that's where it gets kind of confusing, is the output of your controller happens to be the input to your process. So I like to call this the change in process given for the change in the input that caused it. That's it. That's simply what we're looking at. So if I move 5% and it moved 10%, my process gain is 2. And we'll show you some examples. Here's an example. I made a change of 10% and it moved 30%. That's a process gain of 3. Notice I'm using percents here. That's where you'll need to look at your controller and find out, are they scaling the measurement? Are they scaling the output? In the old days, these were in actual customer units, so gallons per minute or liters per minute. Today, pretty much everything is percent, but now you have to enter the span to calculate the percent right. So there's just always caveats. But the thing is you have to calculate, I have a 3. So the question is, that with a gain of 3, let me ask you, if I made a 5% change, what should you expect to see in the actuator, or I mean in the process? Again, I've got a process gain of 3, and I made an output of 5%. Should be 15. It's strictly multiplied. Okay, so that would be what you would expect to see as a change. In this example, I did a 10% change, but I only got a 3% change in the process. So in this example, my process gain is 0.3. Remember when I was talking about earlier the teeter-totter? If you think of the process gain right in the middle, you get, if I make a 1% change, I get a 1% change in the process. It's the teeter-totters right in the middle. If I slide the teeter-totter over and I get a, make that smaller, that means that a 1% change results in a 0.2% change. If I slide it over 1%, that's sort of valve size. That's why I really like to start adding human terms to what we're looking at. Is the process gain has a lot to do with the strength your actuator has on the process. Think garden hose, fire hose from a, how much do I move the actuator for a given air? If you don't know that, your controller will never figure it out. So you have to figure that out. And another thing that you'll see is, and we'll get into nonlinearities, is the valve curve. Where should your valve be during your bump test? There's the 30-60-10-90 rule, which we'll talk about in nonlinearities. But if your valve is in the 50 to 70% range, it's probably pretty reliable. When you get up into the 80 to 100 or 0 to 10, you're in a nonlinear range, and you'll get different answers for this process gain. It can be dramatic too. That's why you do more than one bump test, and that's why you do them over time, so you can record, well, I was at 50% and I got this number, now I'm at 70% and I get this number. Depending upon where you're at in the curve, your process response can be very, very different. That's why you have to have a track record. Pure gain processes are very uncommon. Matter of fact, in today's world, you probably will never ever see one. However, this one is where we're going to, is the first order process. Although this is ideal, it doesn't happen in the real world. It can be used to approximate processes incredibly accurate. So what we're seeing here, again, the math, try not to get too worried about the math. The way this is read is this is a first order, and its roots are back to differential equations. And I know everybody freaks out when I say differential equations and calculus and all that stuff. But the solution to the first order of differential equation is this. So in math, this thing governs. And the way you look at it is, assume this term here is not here. This minus x, that exp is e to the minus t over the time constant. So the way this looks is, as the time grows, this term goes to 0. And I end up at the steady state change. So the steady state change is, well, how much did the process move, which is what I'm talking about. I made a change, how much did the process move? That's this process gain in this 1. This 1 represents the steady state component. The k is the gain multiplier. This represents the dynamic transition time. Sometimes they'll refer to it as settling time or dynamic transition time or lag. It's how long of a lag. This is called an exponential curve. So what happens is, this is the dynamics component. Still, that's a lot of math, but that says is when I make an input change right here, boom, how long will it take for that input to work itself through the process? And you'll get a response where your total change is a function of this gain, and the time it took to get there is a function of that time constant. We're going to spend just a little bit of time on the math here on how to get that. The steady state change isn't so hard to find. It is identical to the pure gain process. That's why we started there. Is here you made an actuator change, you moved it 5%. Again, remember, you worked with the operators, you figured out what a safe value was. You're not bumping in one direction, you're trying to stay close to where you started from. You don't want to make defects. You don't want to mess up on your first bump test, because it'd be hard to get them to let you do the second one. So you did your bump and you see this thing come up. So the total time it takes to get there, that total time, the total change in the measurement divided by the actuation that produced it, that's the process gain. Same as before, same definition. The one that's a little more tricky, I should mention, you can have a negative process gain. Remember we were talking about direct and indirect acting? This is why. And it has to do, if you think of a single-seated globe valve, it has a diaphragm. If they have air going in the top, air maybe closes it. If air goes in the bottom, it opens it. So based upon where the air is entered into the valve, you can flip it from plus to net minus in the process gain. There's other, like in consistency, where if you add water, the consistency changes in the opposite direction of the input. So you can have natural occurring negative process gains. If you're, like an example I said earlier, like if you're driving a car, and you're off in the left berm and you want to move over, you wouldn't turn your steering wheel to the left to try. That would kind of be tough to drive a car like that. So you need to know, and that's where visual inspection and the bump test is a great way to identify that. Now the dynamic transition time is from the time I made the change. How long did it take to get there? Now there's a couple different theories here. There's about 2 or 3, and I'll show you the quick and dirty one. And I still recommend that you do a few of these by hand. We do have an application called LoopTune where if you can collect these data with OPC data, there's data logging, there's so many techniques for collecting this data, loading it in and best fitting a model. They're awesome. But if you don't know how to do it by hand, then those methods are really challenging. There's really a couple different things. The way I like to think of time constants, because it's an exponential decay, and again, I'll just jot back here, sorry, but remember, this is an exponential decay. What you can see here is everything is related to this time constant. So everything's scaled to that. So in one time constant, where's the process going to be? All right. So right here, we can see mathematically, and if you want to plug it into your calculator, go ahead and you can do it. But at one time constant, you are at 63.2% of where you're going. At 2 time constants, you're at 86.5, 3 95.4, 4 98.2, 5 99.3. What I have found is my eye can't tell the difference between 4 and 5 time constants. It's very difficult to see. Plus, it's easy for me to divide by 4. So whatever your total time is, divide it in half again, and that's the number for your time constant. That's the one that says, well, how fast is this going to remove? You know, I've got the strength of my actuator, but how long does it take for that strength to fully be realized? Okay, that's what we're talking about. The time constant, or the lag, is what defines that. The time constant units needs to match the time constant of the integral time of your controller. I'm just going to keep hitting those in and we'll remind you. But if your controller has repeats per minute and you use seconds, you're going to be off by a factor of 60. So take a look at your controller and look at the integral value and see what the units are. Seconds or minutes, typically. And whatever those units are, that's what the units of your time constant are. I like this technique is you take the total time divided by 4 and that gives you a time constant. Again, it's fairly easy to divide by 4. Here's an example. I moved at 10% and it moved 30, but it took 80 seconds to get there. So what are the two numbers that define those question marks? Well, it's got a process gain of 3 and it's got a time constant of 20. 30 over 10, the change in the process, the steady state, divided by the actuator. 30 divided by 10 is 3. And then how long did it take? The dynamic transition time divided by 4. Okay, and that's 3 and 20. Those are important things. I'll just kind of give you a peek under the tent. Is the process gain is related to the proportional gain of your controller, and your time constant is related to the integral time of your controller. So by identifying these, which are a function of your process, those are the cornerstone. Those are your calibration parameters for your tuning. Then all that's left is for you to define, do you want it to happen fast or do you want it to happen slow in terms of when I change the set point. That's why these are so important. Here's another example. I moved 10% and it took 12 seconds to get there and it moved 3%. So I've got a process gain of 3 divided by 10, 0.3. 12 divided by 4 is 3 seconds. So I recommend that you do 2 or 3 of these bumps and try to calculate these, and then usually I'll do 3 or 4 and I'll look to see if they're fairly close. There's rules for fairly close, but you'll start to sense, and if you can predict where it's going to go, then you have it. That's the secret. I like this one too. This sort of helped is if you imagine your time constant, it's sort of like the initial slope. Once it starts to go, where it intersects where you're going is one time constant, and then that slope. And then once you get up here to 4, you're pretty much at steady state. So that's another trick. And then there's a third trick, which is this one, where 63.2% is where one time constant is. 2/3 is 66%. So with the error in your process, the difference between the 2/3 method and the divide by 4 is 2 or 3%, which is not that big a deal. So a lot of times when I'm first starting out, I'll do a bump test. I'll take the total time divided by 4, and then I'll take the total change divided by 3 and figure out where they intersect. And that time is one time constant. So that is a very important number, is the time constant and the process gain. Those are the cornerstones to tuning. If these things are moving all over the place and they're not predictable, you're going to have a very slow tuning response. If these are predictable, then you can be much more aggressive, and we're going to talk about that. Dead time is, or a delay is, you made a change and it took time before the process started to move. And that's all this feature right here says, this is our delay. So as complicated as this equation is, there are three model parameters. There's the delay, the process gain, and the time constant. So what are those? Well, we know the process gain is the change in the actuator and the change in the measurement. So how much did the process gain is that ratio? That's important because that's related to your proportional gain. We looked at the time constant, which is your total settling time divided by 4. That's related to your integral time. Now what's delay? So here you've got a case where I made the change and there's a transport distance. It's very important. Transport distance is usually a function of how you piped it. Where's the transmitter and where's the actuator and how far apart are they? If you have the opportunity to take delay out of your process by the installation of your actuator, you need to do that. Dead time is a destabilizing process. It's dead time. In other words, you made a change and nothing happens. So your controller's like, hey, I thought it's like, imagine driving your car and you turn your steering wheel and you have to wait 5 minutes for your wheels to turn. Well, that'd be a challenge. The same thing can happen in process control. And usually think of a conveyor belt. Something goes on one side and then it has to wait and come off the other side. Anything that has that kind of process hold-up time is destabilizing. But you need to identify it. And there's rules that if the dead time gets so big as compared to the time constant, then you have to use a different control algorithm. Right now we're going to assume we can use a PI or a PID feedback loop. But still, nevertheless, we need to identify what do we have. So delay is simply that. From the time I made the change, how long did it take before that change started? That's my delay. That's what we have to identify. So here you can see what we're showing is an example where we have a valve change and it took a little while and then it started. There's three parameters here. There's the how much did it move, process gain, how long did it take to get there, the time constant, and then when did it start to move, the delay. So I also want to pull back a concept that we talked about earlier, which was model mismatch. On some processes, the relationship between this delay and this time constant dictate that you have to go to a more elaborate control algorithm. However, there's a lot of systems out there that we can still use our trusted PI algorithm, and that's what we're going to try for. But we have to realize this isn't the model that a PI algorithm sees. The PI algorithm sees a pure first-order model. So we have to identify this thing called model error. So this is what a PI-tuned loop assumes is going to happen. So what we have here is the process gain is the same. Notice it's the change in the measurement over the output that produced it. So in a two-parameter model, that's the same. But notice we're ignoring the dead time because the dead time is being wrapped into this time. So this little prime here is a fake time constant. We're saying, yeah, that's a prime, process time constant prime. It's not really the time constant of the process, but if I take 4 of those, 4 of these gets me to the same place as the dead time plus 4 of these. Does that make sense? Just real quick. This is the actual time. I'm showing you here, you have your actual dead time, your actual time constant, and your actual process gain. If I were to show a dotted line up here, this would be your sort of your fake process. The fake process has a time constant that's equal to this total delay plus 4 of these time constants all divided by 4. And that's this equation. And we'll talk about that as we go. And this model mismatch or this model error, if it gets too big, you'll know, and we'll talk about that when we get into the tuning techniques. So, two-parameter model is used when delay is not dominant. Using a two-parameter model for first order, you perform a bump test, you record the process response, you fit a first order approximation, and you determine the process gain, how much, and you process time, how long did it take to get there. That's really it. And you need to make sure it's repeatable. Make sure that it happens. So in this example, we'll end up on this. We're going to do a bump test. So you can see this is a trend you might be watching. And you can see here it goes. We're doing this bump test, and this is a trend that we're seeing. So the first thing is this is a bump. So hopefully you have something like that in front of you. You pick a loop or find a loop and do a bump test. So the first thing is, what type of process is that? Is it a first order, pure gain, second order, overdamped, underdamped, critically damped? Go back and look at those 6 screens. This happens to be a second order overdamped process. That's all you need to know. But what we're going to do is assume that it followed this dotted line. Okay? Then what we need to do is say, well, how much did it move? How far did it go? It changed 25%. How much did I change my output? 15%. So what would the process gain be? 1.67. That's the number. File it away. Now I need the time constant. Well, how long did it take to get there? This is going to take you a little while, but figure out total time. In this case, I'm saying 50 seconds. That's about when it got flat, 50 seconds. At 50 seconds divided by 4, that's 12.5. That's your time constant. Those are the two numbers. It can be as easy as that. And I would recommend doing 2 or 3 of those bumps to see if you're coming up between, if you're coming up with 1.67, 1.7, 1.55, then you know it. But if you do one time you do your time constant is 12, another time it's 80, well, you may need to go look at the hardware and do a physical inspection and find out why is this process model changing so much. Once you identify it's like you've captured this tiger in a box. Now you know what to do, and that's when tuning comes in. And that's what we're going to talk about in our next series.